without further ado, I think, Brice, the floor is yours.
Thanks. All right. So as Gerald mentioned, my name is Brice Exley. I'm a geotechnical engineer with Hart Crowser out of Seattle. I'll be discussing the berth modernization for Terminal 5 at the Port of Seattle, specifically the test pile program. The project is located on the west waterway of the mouth of the Duwamish River, which flows into the bay in Seattle. It's to upgrade an existing dock that's about 2,900 feet long. Part of the project is, or the intent of the project for the upgrade is to allow for the terminal to support ultra large container ships, such as the Maersk Tripoli with 18,000 units. The draft of that ship is 52 feet deep. The existing berth is not uniform in depth and could not support the depth requirements of ships that large. So it requires both deepening the berth and installing larger and heavier crane rails to support larger cranes for those ships, which necessitates new crane rail piles and new crane rails. So the increase design that the port was aiming for was a 85 kips per linear foot design load, which significantly increases the load on the structure. That also resulted in a stiffness sensitive structural model that the port actually had to collaborate with the developers of SAP to modify the program to account for some of our models. So quickly go over the subsurface conditions to kind of give some guidelines or input as to where we got and why we did the testing program that we did. If you look at this profile, we have alluvial soil overlaying glacially overridden soil. In the Seattle area, our glacially overridden soil is extremely dense generally, like 50 for 3 blow counts in a lot of areas. And the alluvial soil is, as typical, very loose. Grading from south to north, north being on the right in this figure, the site has a significant drop in elevation of the bearing layer from about minus 80, 85 down to minus 140, 150 mean sea level elevation. And the bearing layer also changes in material types across the site, which you'll see on this next slide. So we split the site up into 3 separate quote unquote pile sites, kind of following some methodology defined by AASHTO and FHWA, where on the south end, for the first 350 feet, we encountered some very stiff clay with blow counts of about 40 blows per foot. It's our belief that that's related to the Seattle fault as it runs essentially across our site. The middle section where that bump in the bearing layer was actually the densest layer in general. It had a blow count of 50 blows for every 6 inches to every 3 inches. And then as we move north, the blow count generally varied from about 80 to 50 for 6 again. So this is shown here, far left side, we have that stiff clay area that I wasn't completely sure how it would behave. In the middle, we had the very dense sands and gravels with 50 for 3-ish blow counts. And then as we're moving north, that bearing layer gets much deeper and we potentially have to account for more resistance in the alluvial soil and then just try to understand how the driving behavior will change as we get over there. In general, across the site, just above this bearing layer, we also had a very soft clay with single-digit blow counts or blow counts of 0 and weight of hammer. So there was also some concern about high tensile stresses during driving on concrete piles. So to quickly go over what the port's plan was for the crane rail piles, waterside, the port uses pre-stressed concrete piles by practice. They've typically used 18 or 24-inch octagonal piles. For this project, we chose 24-inch octagonal piles to try and get as much capacity as we could. And then landside, we were looking at both 24 and 30-inch diameter pipe piles. Our initial design was based on high strain dynamic testing with signal matching at similar sites that we have collected over the years. The waterside crane rail piles, we had a couple of questions. As I noted, there's a potential for some high tensile stresses in the piles as we transferred right before the bearing layer. We also wanted to get as much capacity as we could, and in order to do that, we knew we'd probably put some fairly high compressive stresses on the piles. And then the high strain dynamic testing that we've done in the past suggested some pretty low beta values, as well as I had a suspicion that it was underestimating the tip resistance because at least by practice, the concrete piles out here have been driven with hammers of the size of like a D62 or smaller in refusal conditions. So you have a good idea that if you think about that, you can only impart so much energy and you can only measure as much resistance as what you're measuring, or as what based on the energy you're inputting. So I had an idea or a belief that if we hit it with a larger hammer, we would be able to observe more capacity. And so we needed to try and explore that to get as much load into these piles as we could for the port. Also of importance was the low deformation characteristics of those piles. As I mentioned, the structure became fairly stiffness dependent. And so we wanted to explore with a high degree of reliability how those piles would behave, specifically the tip resistance, because that's controlling. And then that far south section where we had 40 below count clay or plus 40 below count clay, what would pile driving in that material be like? I knew when we hit the other bearing layers, the piles would essentially stop, but how deep could we drive into that? Landside, as I mentioned, we had pretty low beta values from the existing data that we have, much lower than what you would typically observe from FHWA recommendations for driven pile design. And then what embedment lengths could we get into the glacial deposits with open-ended pipe piles, and will it plug in those deposits? Those were pretty large uncertainties that we had, at least from a sensitivity standpoint, so we needed to explore those. The landside pile design, again, we had a pretty large unknown relating to the load deformation characteristics, and then what hammers did we need to use. Again, our existing database had fairly small hammers relative to what we ended up using for this project. So we wanted to explore what the effects of a larger hammer size would be on the capacity, and could we potentially use a smaller hammer during production. An additional approach we took to determining the capacity of the piles was using a rapid load test. In addition to high strain dynamic testing, the reason being for that primarily was to try and capture, hopefully, a better estimate of the load deformation characteristics of the piles and identify if those steel pipe piles would plug. It's pretty well documented that they may plug under static testing, but not dynamic testing, such as a cap wrap when hit with a pile, as the pile movement can dislodge the plug, essentially. So our load test program had several goals summarized here. Basically, we wanted to try and refine our pile design as much as possible with the intent of eventually reducing the construction costs. So the test pile program included 6 waterside concrete octagonal piles. The port was able to work with a local pre-stressed concrete supplier to provide 10 KSI concrete with some fairly significant pre-stressing and piles that are up to 178 feet long Conveniently, the supplier's on the water, so they just barged them in and never went onto the land. And then on those piles, we did 3 rapid load tests. And then land side, we installed 9 steel piles ranging from 24 and 30 inch in diameter. Some of them had tips on them to close the piles for comparisons, and we tried various installation sequences, including vibratory hammers. Could we install it with a vibratory hammer into the glacial materials? What did that have on what impact did that have on the pile capacity, and so on. So the bid package, like I said, included all of the piles. The piles are supplied by the port, but included all of the piles, the work, the rapid load testing PDA, needing to go and wait for us to do for setup time between the piles and testing, and several hammers. So this is just a quick aerial overview of the project site. The cranes were there, so they had to do a little bit of juggling with the cranes to get them out of the way as we were moving down the wharf. And there was no tenant, so it was fairly easy to work on otherwise. The overall bid price for the test project was about 2.4 million. As I mentioned, the owner provided the pipe and concrete piles actually, but one thing to take into account when you're thinking about the price here is even if we didn't do the advanced load testing that we did do, i.e. the rapid load testing, we still would have gone out and done some form of test pile program for drivability to reduce the risk for the owner. So the actual cost associated with the load testing that we're doing to the port is a fair amount less, but that's not specifically quantified. The pile installation means and methods for the offshore piles. They did a 4 pick point from barge and lofting from a landside crane. They installed the concrete piles initially with a hydraulic hammer as they were a little concerned of hitting it through that alluvium, at least to start, with the D100, which is the large concrete or large hammer we selected to drive the concrete piles. As I mentioned, at least historically out here, we've been hitting 24-inch concrete octagonal piles with D62s and smaller generally. I would note that we're in production and the contractor's using a D100 full length right now. So just a quick comparison of the hydraulic hammer they used for initial drives and then the D100 they used once they had the piles essentially set into the subsurface enough where they felt comfortable. At the end of the project, they had to extract the test piles to allow for continued use and get them out of the waterway. That involved extracting them where they could and then cutting a few piles with this instrument. For the upland piles, they were steel, as I mentioned. We had several hammers, a D62, the Super Kong vibratory hammer, a D2 or a 8250 vibratory hammer, and a D180, which is really what we were going after to try to identify how far we could drive these piles into the bearing layer. Just a quick picture of installations. They were field splicing the piles together in the hole. We also had installed a piezometer within the plug of one of the piles to try and identify how long it would take for pore water pressures to dissipate. There's a little bit of lessons learned there for what we would do next time if we tried that, as we ended up losing piezos, but the data I did have suggested some liquefaction pretty far in advance of the pile toe, which was interesting. For the impact hammers for the steel, as I mentioned, we used a D62 and a D180. Just for a quick comparison, the energy between the two. So a traditional hammer out here, the D62, 161,000 kip feet of energy, whereas the D180 has 443,000. Just a quick picture of driving with the D180 on a 30-inch pile. We did PDA testing with high strain dynamic testing with signal matching on all of the piles. We also did ICAP, so some simplified continuous CAPWAP or signal matching testing to try and get a better understanding of the profile resistances during driving for final design, which was able to inform us about the capacity of some of the existing piles on the project. So if you're not familiar with rapid load testing or statnamic testing, basically you go through, stick a large series of weights on the top of the pile with a catch system. There's some fuel that you ignite and push up on those weights, which using some basic laws of physics pushes down on the pile. You measure the forces in the pile and the displacement, and you get a low displacement curve. There's a little bit more to it than that, but that's really simplified answer. A quick picture of the dynamic testing, building it up. Basically, it's in a squat rack with the weights being assembled in here. Our results, which is what most people are probably curious about, were pretty interesting. The concrete pile, we loaded a 24-inch concrete pile up to 2,100 kips here with the rapid load test, and it moved about 1.9 inches at the head. As you'll see, that's linear. We didn't fail it. We ended up sequentially increasing the pile or the load in statnamic test as we did our 3 tests above what the structural engineers were initially comfortable with, and we ended up just basically being limited by the structural capacity of the piles for testing. So this is some output from our TZ results for the piles. So the side shear along the depth of the pile. Again, we didn't see failure for at least the bearing layers up in the alluvium. We clearly failed the soil. Toe resistance, again, we didn't fail it. That went all the way up to, it's not on this plot, but another one of our piles, I believe we tested to 567 kips per square foot. So it's a pretty massive end bearing resistance that we were able to measure. For the steel piles, again, we didn't fail these either. This shows the pile going up to 2,200 kips test load with primarily elastic deformation of the pile, to be honest. So our final concrete pile results, like I said, we installed we ended up installing 5 concrete test piles. We did rapid load testing on 3 of them. A quick comparison between the rapid load test and the CAPWAP. The rapid load tests showed basically as much load as we could put into the pile. So the CTP6 is the last pile we did where we said, hey, let's get all we can out of it. We're not worried about breaking the pile at this point. We measured 2,560 kips of total resistance, almost 2,000 kips of end resistance. That's the one where I said we measured like 570 kips per square foot. The high strain dynamic testing in those refusal conditions with the D180, we were still, or the D100, sorry, we were still much lower, and that's, again, I suspect just primarily due to refusal conditions with the pile during driving. The steel test piles, it was a similar conclusion. We had to limit our loads on the steel test piles as there was a complaint from a neighbor midway through the program. They thought that their slope was, or their house was moving due to vibration. It wasn't, but the port was very concerned about the PR. The overall project goals, we ended up significantly increasing our resistances. We reduced the uncertainty in the load deformation characteristics. We were able to observe a pile toe in the steel piles, which resulted in some pretty large economic benefits for the port. So as I mentioned, the test pile program had a total cost of about $2.4 million. The port's estimate is that just in material costs, essentially, that saved them about $4 million. It also significantly improved their tight construction schedule with working with in-water work. The project's spread out over 3 in-water windows right now, And if we had to increase or decrease the pile spacing, that probably would have spread into a 4th year. It also proof of concepted the pile structural capacities for the port. So as I mentioned, they were able to work with the local concrete supplier to get the piles up to 10 KSI to allow us to install these piles with this large hammer. And then from a less quantitative standpoint, but probably as important, if not more, for the port, is it had a pretty significant environmental impact for them. So we have much fewer blows in the water. We have less in-water work, obviously, and the port has an agreement with local tribes to allow fishing under the dock. So having the larger spacing of piles allows the tribes better access beneath the dock. That's about it. This is a quick overview of all the companies that were involved with the test pile program. AFT and Burt Miner were pretty instrumental in performing the load testing, as well as specific pile for installing the tests.
Okay, Brice, thank you very much for this interesting presentation. And also, as you put in your previous slide, you had a test program that was roughly a little bit more than about 60% of the savings that you achieved. So there was the test program in the end, it didn't cost anything on top, or more strongly, it actually saved money, and that's what this presentation is all about, and this webinar series is all about.